And our lecture should be recorded from now on. So this is March 23rd, 2020. This is Geo 319 surface processes. And this is our first post class closure online lecture. So I'm gonna share my screen here, and I think you guys should be able to see my PowerPoint. Presentation. All right, so let me know if you can't see that PowerPoint, but I think everybody should be able to see it. I'm gonna see if there's a way I can check texts or chat. Well, there we go. Okay, so I'm sharing my screen. I can see participants and I can look at chat. So if you have a question, you can either just unmute your audio and talk at any time, or you can check the chat. So Mark just asked permission to record. Mark, I'm recording this, so you'll be able to download and view this at any time. So you don't need to record, I'll record it. It's being recorded right now. Probably take me, I'm guessing, an hour or so to get the video posted on Moodle, but every lecture from now on will be recorded and posted on Moodle. Another announcement, I'll do my office hours Tuesday, Thursday at 10. I'll have a Zoom meeting. I'll send out a recurring invite, so you can just click on the link, and I should be available every Tuesday and Thursday at 10 for any questions and chats. Okay, so I hope everybody's doing well and that you're surviving the quarantine mode. I hope everybody's as safe as possible. So today we're gonna start lecturing, and just the caveat is that still learning how to do some of this lecturing and how to take our class online. I've got some new technology that I'm trialing. In particular, being able to write on the computer screen itself without a whiteboard. So I'm not real great at it yet, so don't expect any perfect art. But I tested over spring break and I was able to annotate, and all those annotations get recorded. So I think all of these, all this writing will be recorded on the Zoom lecture recording. So for now, let's just move forward. Again, please jump in if you've got questions, and feel free to talk or text. Okay, so we're gonna move forward. Today what I wanted to do was chat about cycling of carbon, nitrogen, and phosphorus within the critical zone. We're gonna think about these cycles a bit more, and then on Wednesday we're gonna introduce a new technique for tracing these kinds of interactions in the critical zone. That's stable isotope methods. So today, what I'm really trying to do is just build more background of carbon, nitrogen, and phosphorus cycling and focus in on the critical zone itself. So let's see if I can. Okay, so we're going to focus in on the carbon, nitrogen, and phosphorus cycles. And the major interactions within the critical zone. And I want to start to highlight ties between these cycles and how we can think about changes in one cycle affect changes in the other cycles. And in particular, how critical zone processes can start to affect these cycles. Okay, so we're going to start off looking at the critical zone or the carbon cycle, the global carbon cycle. We've looked at these kind of systems diagrams for the carbon cycle before. I'm going to see if I can find my, oh, there we go. All right. So, you know, the main processes, the main processes that we talked about already, and the ones that I want you guys to focus on are these processes of, let's see while I figure my stuff out here. Okay, so the main things that we want to talk about are soil respiration and plant respiration. So respiration in general. And then the opposite of respiration is photosynthesis or production. So we can think of respiration and photosynthesis as opposites. So respiration, well, let's start off with production. So I'm learning to write on the computer, and it's not pretty yet, but it's getting better, believe it or not. All right, so production is essentially the production of oxygen. So we take CO2, we add sunlight or energy, Adam tells me that the writing is not showing up. All right. Let's see if I can do it another way. It did show up on the recording, which is funny, but it's not showing up now. Let me see if I can do this annotation another way and whether it will show up. So tell me, can you see the drawing now? So production. Okay, I've got, looks like people can see this writing now. It's not as good as the other form, but it'll work. Okay, so so production is we take CO2, we add energy, and we produce oxygen and water. Okay, so that's photosynthesis or production. So the opposite is respiration. So we got soil and plant respiration. And respiration, we take organic carbon. So I'm going to call that C organic. We use oxygen and we produce energy and CO2. Respiration. All right. Okay, so one of the things that that I want you guys to focus in on or understand is that the role of oxygen is really important. So respiration in general will use up, respiration will tend to use up oxygen. So respiration consumes oxygen. And that becomes important in water bodies or in soil. When we have a lot of organic carbon, microbes and other fungi and other organisms will break down that organic carbon, and to do that, they use up oxygen. Production, on the other hand, produces oxygen so when we have photosynthesis, we can increase the oxygen in our system. One example of these coupled processes is in rivers and lakes. We get a diurnal cycling of oxygen in the water body. So if I was to look through time, so here's time. And let's say this is on the far end, this is 1 day. If I was to look at the oxygen content in the water, the amount of oxygen, let's say we're starting off at midnight, so we're at the night, middle of the night here. We would start off with low O2. As the sun rises, we'll see an increase in dissolved oxygen in our river. It'll peak at about 3 or 4 in the afternoon, and then it'll come back down so that at nighttime it's descending again. And this is because the algae in, so let's call this right here, this is noon. It's because the algae start turning on when the sun comes up. They start undergoing photosynthesis, producing O2, and increasing the dissolved oxygen in the water. Once the sun goes down, photosynthesis stops and the oxygen is consumed by microbes that are using up any organic carbon, such as leaves or litter fall, any kind of organic carbon in the river. They start to use up that O2, and it comes back down during the night. So we see these diurnal cycles in streams where the O2 starts low in the morning, and by midday or mid-afternoon, we have a lot higher oxygen content in the water. Then it goes back down at night. Okay, so this process of production and respiration is the primary sort of fluxes of carbon in and out of the critical zone. So let's now see if I can get the page to move. I'm going to clear my annotation, clear all drawings. All right. So now what I want to do is start focusing in on the critical zone. Remember, the critical zone we defined as this area from the top of the vegetation down to the bottom of active water circulation. But we want to think about carbon cycling within the critical zone. And again, the dominant processes are going to be this photosynthesis and respiration. And then we think about how these processes happen in the critical zone. And in principle, the critical zone is sort of most actively or best represented by the soil. This is where all of our different spheres of the critical zone, say the atmosphere, the geosphere, and the hydrosphere, are all interacting. And so the soil is really the hot spot, I'll say, of the critical zone. Okay, so we take up atmospheric CO2 via photosynthesis, all right? And that creates organic carbon and energy. So we get organic carbon from photosynthesis in the roots and in the leaves. That organic carbon, everything that lives, eventually dies. And so we get humus, or accumulations of organic carbon. Those accumulations of organic carbon get decomposed by the various soil microfauna and microbes, any fungi in the soil. All right, so decomposition and respiration takes that organic carbon and produces CO2, which can then go back into the atmosphere. All right, so these are the main cycles of carbon cycling in the soil. What's important to remember is that in order for this decomposition reaction, we require some electron acceptor, and that's usually oxygen. So it requires O2 most of the time. Okay, so that's the general soil carbon cycle. The main things I want you to focus in on are production or photosynthesis, right, and respiration, and then how photosynthesis produces the oxygen, and then respiration consumes it. All right, any questions on carbon cycle? I don't think it's anything that we haven't covered before yet. All right, then we'll move on. and talk about the nitrogen cycle. All right, so by far most of the nitrogen is in the atmosphere as N2. And N2 is really non-reactive, so it's very stable. So in order for nitrogen to become part of the biogeochemical cycle, we need to have bioreactive nitrogen. So I'm going to give that the symbol N sub R. And that's bioreactive. Nitrogen. All right, so we need to produce bioreactive nitrogen one way or another. And the natural way that that's done, so the natural way we produce bioreactive nitrogen from N2 is fixation. And that's done by plants or microbes that can break this stable N2 bond and create bioreactive nitrogen, mostly in the form of ammonia. The other really important process that actually isn't in this diagram at all is the production of fertilizer. So this is not really a natural process, it's an anthropogenic process. So the production of fertilizer, and that uses what's called the Haber-Bosch. And this is production of fertilizer or bioreactive nitrogen. And basically what we do is we take N2 out of the atmosphere, we react it with hydrogen, so 3 hydrogens, and a ton of energy. And we create two ammonia atoms. So this Haber-Bosch cycle was invented during World War II. So here we take this nitrogen, we put it usually in, we combine it with methane or hydrogen gas. We put some metal catalysts in there. We do it under really high pressure and add a bunch of energy, and we produce bioreactive ammonia. And this Haber-Bosch cycle has completely changed the global biogeochemical cycle. So now we, or humans, through this Haber-Bosch cycle, we are fixing a bunch of nitrogen and producing bioreactive nitrogen that we can then put as fertilizer on our fields. All right, so this is a really important process. One of the things that's interesting about this process is that the source of the hydrogen usually methane or natural gas. So this coupling right here, this couples our carbon, at least the anthropogenic carbon and nitrogen cycle, because we need methane or natural gas or various different hydrocarbons to produce our fertilizer. Okay, so we create bioreactive nitrogen either via fixation naturally or via the Haber-Bosch process. We add this bioreactive nitrogen to our system, and then it gets taken up into the critical zone system. So let's focus in on now on the soil nitrogen cycle. If I can get this screen to move. All right, there we go. Okay, so you've got this, you've seen this picture before. This is the soil nitrogen cycle. Again, the soil sort of is the hot spot of the critical zone where a lot of this nitrogen cycling is occurring. All right, so we have natural addition of atmospheric nitrogen via fixation. So these guys fix nitrogen. We can add it also. It's not even on this chart, but we can also add fertilizer. To get more bioreactive nitrogen. The major processes that we have, once we're in the soil and we have bioreactive nitrogen, one is ammonification. So that is taking, say, N2 and creating ammonia. We can also decompose existing biological material and create ammonia. So there's two main ways we create ammonia, one from decomposition and one from fixation. All right, so this process consumes, well, this process here consumes oxygen. All right, so we have to use up oxygen in order to decompose or respire this carbon, and we produce ammonia. All right, if we've got ammonia and we have oxygen, so here we can nitrify our ammonia. So this requires oxygen. All right, so if we've got oxygen present in the system, we can nitrify our ammonia and create nitrite and nitrate. The difference between these two is just how many oxygens are on our nitrogen. All right, either 2 or 3. It's just this difference is actually called an oxidation state difference. And then you can basically think about it as how many oxygens there are and how many electrons the oxygens have taken. All right, so we can produce these nitrites and nitrates, all right? And then they can be assimilated into plants, all right? Bunnies can eat those plants. And we can eat those plants. And then we can get decomposed and enter the system again. All right, so we have to fix nitrogen. If we don't have oxygen and we decompose, or if we decompose, we consume oxygen and we create ammonia, all right? If there's oxygen present in the system, that ammonia will become nitrite or nitrate. So the main things I want you guys to think about are these main processes of fixation, decomposition, ammonification, and nitrification, and how oxygen controls what state nitrogen might be on. All right, so Wendell is asking me if nitrifying bacteria extract energy or put energy in. That's a great question. So, so here's what actually happens. So they are extracting energy. What they're doing is when you or I or any aerobic organism respires, right, or undergoes respiration, we took our organic carbon and we used oxygen to as the electron acceptor to gain energy. What nitrifying bacteria are doing is breaking down organic carbon by using ammonia as the electron acceptor. So you can think about it as they're breathing ammonia. And so they're undergoing carbon decomposition. They are essentially breathing the ammonia, and they're producing their energy by breathing that ammonia. Okay, so any other questions about the soil nitrogen cycle? All right, so one of the things that we're going to move into is, and we talked a bit about it last week in our lab, is trying to trace the movement and the source of nitrogen within the critical zone. So in our lab on Friday, we looked at salmon as an allochthonous source of nitrogen to Pacific Northwest river systems. So here we're going to, we can think about all the different places that the nitrogen comes from, and then starting on Wednesday, we're going to look at using stable isotopes to trace where nitrogen comes from within these different reservoirs and pools, and look at food webs or look at how nitrogen is moving through the system. Okay. All right, so the next one I want to focus in on is the phosphorus cycle. We haven't talked a lot about the phosphorus cycle yet. All right, there's the main sources of phosphorus to the critical zone are essentially dust deposition. So we've got deposition as a source, and then the other one is weathering or dissolution of minerals, right? And then fertilizer. So the way that humans get fertilizer or fertilizer phosphate is by mining. So we mine apatite. All right, and we produce fertilizer from that. And that's really, you can think of it as just accelerated dissolution or weathering. So basically we add phosphate either via dry deposition or from rocks. So rather than an atmospheric source, the main source is from rocks and minerals. So we'll focus in on what happens here in the critical zone, but it's essentially mostly driven by mineral weathering, and then uptake of bioavailable phosphorus, which is in these are the bioavailable forms here, these phosphates, these oxidized phosphates. So they require, you can see here they've got oxygen. So the production of these requires oxygen because we got all this oxygen here. So these are the oxidized forms of phosphorus. All right, so let's see. So let's focus in on the soil. Here. And look at the phosphorus cycle in the soil or the critical zone. All right, so we add phosphorus to our soil zone by adding fertilizers. So animal manures, biosolids, or synthetic fertilizers, which come from mined phosphate. Those go into the organic phosphorus pool. And this process where we create soluble phosphorus via these phosphate atoms, that's called mineralization. And these get taken up by plants, all right? They can then also precipitate into secondary minerals. So a common one is this iron phosphate. These ones are not bioavailable, so this is one way we remove phosphorus from the system. And we can also absorb them to clay surfaces. But all of these are sort of locking the phosphorus up in minerals. But the main cycles here are taking uptaking the phosphorus into plants, and then the decomposition of any kind of organic carbon into or organic material into organic phosphorus, all right? And then we can add more phosphorus by leaching naturally occurring primary minerals such as apatite. And we can remove phosphorus by adsorbing to clays or creating secondary compounds such as iron phosphate. Okay, so here the one of the things to think about is that in order to produce this organic phosphorus, we need to decay material. So this consumes oxygen. So this is done via decay or respiration. And then that decay allows us to mineralize it, produce the soluble phosphate that plants can use. All right, so lots of, so one of the things that I wanted to get to today is that all of these processes are highly connected, all right? And they're connected largely via the oxygen cycle and the availability of oxygen. All right, so for the last few minutes of class, what I wanted you guys to do is have a think about this observation. And that is that when we increase bioreactive nitrogen from fertilizers in a watershed, we often see an increase in methane emissions from wetlands. And I can see here that I did not include the wetland carbon cycle. So I'm gonna throw up a image of the wetland carbon cycle here in a sec. And what I want you to do is to use the systems diagram from this wetlands carbon cycle and give me some explanation of how you think the addition of this bioreactive nitrogen would cause an increase in wetland CH4 or methane. All right, I'll throw that up right now so you have the last 5 minutes of class to look at this. I'll also post it on Moodle. And then just turn in a short paragraph answer via Moodle on how you think these two are coupled. The main thing I want you guys to do here, one is to just get some class interaction and some feedback. And then start you guys thinking about how these different geochemical cycles are connected. So how is the carbon cycle of a wetland connected to my addition of nitrogen via fertilizers? All right, so let me just end my PowerPoint slideshow somehow. And I'll throw up the wetland let's see what's happening. Carbon cycle image. All right, so can you all see the wetland carbon cycle image? Should make sure that's happening. Oh, I think it should have crashed. Hold on. Share desktop. Okay, I think you should be able to see my desktop now. So I can pull up the carbon cycle. All right, so I think you guys should see the carbon cycle. Let me know if you can't. So this is the wetland carbon cycle. It's very similar to the previous carbon cycles that we looked at. We have uptake of CO2 via photosynthesis, all right, decomposition and decomposition, all right, and one key here is one of the final end products of decomposition is methane. All right, so one paragraph, few sentences. How does addition of bioreactive nitrogen increase methane emissions from wetlands? You can, Mark is asking, what is DOC? Can you guys see the writing now when I write? So can you see me writing here? So DOC is dissolved. Organic. Carbon. Another thing you'll see a lot is DIC. That's really this guy here. DIC. And that is, guess what? Dissolved. Inorganic. Carbon. All right, so we're coming to the end of class. I'm gonna give everybody I'll stay on the line for another couple minutes to answer any questions. There's a Moodle assignment that you can turn in this paragraph, this class assessment activity. Please feel free to email me any other questions. One of the things that I wanted to make sure that that I was very transparent with is that the feedback between you and me as we figure out how to transition to online classes is really important. So if something's not working, if you have other ideas for how to better implement some of these courses, please let me know. We're all scrambling and trying to figure out how to do it in real time. So any feedback you can give me will help us improve the class faster. So feel free to reach out via email. I will post all of our lectures recorded on Moodle. And then any in-class activities will have a Moodle turn-in assignment. Andrew and I are going to work to try and get all our labs and graded assignments up so you can get a better idea of your grades as soon as possible. And we'll just try and keep the amount of information flow as high as possible using remote systems. So feel free to email me with any questions. If no one has any other questions, you want to text me right now in the next minute or two, then I will stop my recording, and we'll talk to you Wednesday and talk about stable isotopes. All right, I'm not getting any questions for right now, so I hope you all are doing good, and we'll talk to you Wednesday. This will end our lecture for today.